Welcome to the Ray Served and Data LLM Office Hours. I'm Seiji, and I'm going to be presenting on our YDP and disaggregated serving APIs that we recently introduced in open source Ray. So the first part is this. I think the best way to do this is just, let's see, is my screen sharing? Just checking on that. It's coming through. Cool. I think the best way to do this is I'll just walk through our recent blog post, drop it in the chat for now. And so I'll walk through the blog post, kind of high level, how it's structured and some facts about it. And then next I'll go into a brief demo, talk about how it's set up. And if folks have any questions, feel free to jump in and we can cover that. But yeah. Okay, so let's start with so briefly, RayServe LLM is a super ergonomic way to deploy VLM inside a Ray cluster. Anywhere you can run a Ray cluster, whether it's a VM stack, uh, hardware, nodes, Ray, or Anyscale, which is our hosted Ray offering here at Anyscale runtime. And YDP is a specific way of serving VLM engines, so in a particularly optimized for sparse MOE models. And disaggregated serving is an orthogonal but related serving method that's also really helps improve sparse MOE model serving, but also model serving in general high throughput scenarios. So that's kind of the intro. Um, and from there, we validated these results on any scale runtime. So we got up to about 2,400 tokens per second for H200 serving DeepSeek v3. So just some kind of napkin math for you to reference. And cool. So I'll finish this by talking about the design and architecture of YDP, so why you would need it and what it would look like to deploy it in with RayServe LLM. And then I'll go to disaggregated serving, briefly cover that, and move on to the demo. So for YDP, it takes this kind of technique you may be familiar with, expert parallelism, and combines it with data parallelism and other large-scale serving optimizations like specialized all-to-all kernels. And we kind of call that wide EP. So whereas just expert parallelism, maybe you'd combine it with tensor parallelism and you'd shard one copy of the attention layers across multiple GPUs and split one set of replicas across all those tensor parallel ranks. YDP combining expert parallelism with data parallelism means replicating your attention layers across ranks and then splitting your experts amongst those ranks and sharing them amongst those as well. And so the benefit for YDP, especially um, for models like DeepSeek, is that you don't replicate your KV cache across ranks. So this is like for maybe offline if you're not familiar, but DeepSeek models use a multi-head latent attention architecture, and so each rank needs to compute that latent projection from the attention layer for KV cache. And if you go with a naive route for expert parallelism with tensor parallelism, each TP rank has to maintain a duplicate copy of that MLA latent projection, which means that ultimately you only have uh, you you only as much like you only have as much KV cache across the whole expert parallel setup as you do on a single TP rank. Um, but yeah, so the benefit, so then the like optimization that DeepSeek introduced is to replicate the attention layers on each rank, and then just say, okay, well, because yeah, the KV cache is already replicated, so let's make sure each rank can handle requests independently. So that's YDP in a nutshell, and it requires this coordination between DP ranks. And that's why I have it this diagram here. So in a Ray cluster, what this would look like is a set of worker nodes, and then this comes from Ray serve, the HTTP proxy, and this just is the like component that will handle distributing your like incoming requests across the deployments in the serve deployment. And on each worker node, you'll have some amount of DP ranks. So these, like I mentioned before, are the uh, ranks that replicate the attention layers, and then those will each have an async LLM, a Ray distributed executor that attach to the Ray workers. And so they all are coordinated in their rank number and host port via the uh, oh, okay, nice message in the chat. Let me share this link again for anybody that joined. Um, and yeah, and we're recording this as well. But so all of these DP ranks are coordinated by the DP rank designer. And what that means is it's really easy to deploy this. So you can build a DP, a YDP deployment with something as simple as this. So a few lines of Python after you set up your Ray cluster and run this with Python serve DP. So all right here. And and then yeah, so cool. So that's YDP. And then the upshot basically is that YDP deployments let you maximize KV cache with attention architectures like DeepSeek's multi-head latent attention, because you use the fact basically, or you get around the fact that KV cache is duplicated when you shard the ranks, when you shard the attention layers. Cool. Yeah, so feel free to drop questions throughout this at any point, but I'll move on to disaggregated serving. So disaggregated serving has been around. It was introduced about 18 months ago, first by the How AI Lab, I believe. But in a nutshell, it's this idea that it takes this observation that the prefill and decode stages of LLM inference have very different profiles in terms of their hardware needs. So, quick refresher: prefill is the point where is the stage of inference where we're processing prefill tokens and generating KV cache. And in particular, prefill tokens are processed all at once. So we usually call that compute bound because they all get sent to the GPU at once, and then all the streaming multiprocessors can operate them simultaneously. Um, and so what that means is we're getting really good utilization out of our GPU flops. Whereas in decode, we only one, if you recall, only one token is processed at once, and they are processed, one by one sequentially. And so the amount of compute that they require to produce those tokens is actually very low, and the limiting factor in terms of output throughput is just the throughput of your high bandwidth memory, basically. So we want to we want to if we but yeah, okay, so that's the difference. And the issue when you mix those is that suppose you have a batch of 10 requests, and one is a prefill of 5,000 tokens, and then nine are just in the decode stage trying to produce one token. So if you mix them in a batch, then what you'll see is that your decode token throughput, or your total throughput, will be limited by that long prefill time as that 5,000 token input sequence is processed. And what you'd like to do, ideally, is to have one engine replica handle all of those all of those prefill. And if you have a workload that is particularly has a where you expect to see really long prefills like multi-turn chats or agentic flows with a lot of tool calling, then you can scale your prefill replica deployment independently of your decode, and just have them communicate the KV cache to your decode workers to like pump out those output tokens as soon as the prefill's ready. but yeah, so that's disaggregated serving, and the again, like the benefit is splitting prefill and decode. There's an additional benefit for our sparse MLE models, or when we have a wide EP deployment. The two benefits are that you have a um, one that you have the in a wide EP deployment, you can have the ranks need to complete a forward pass simultaneously, or in synchronization. And that's because your experts are distributed across ranks, which means that you could, as a token is processed through a rank, it could jump from rank to rank to get processed by different experts. And so so that means that the forward passes need to synchronize. And it also means that if you have a one pre-filled lagging, like I mentioned earlier, in a single batch, it's not only going to affect that particular data parallel rank, but all of the data parallel ranks in the entire deployment. So the benefit of disaggregated serving is amplified in that example. And then the second reason is we have, like I also touched on this, we have special or DeepSeek released the specialized all-to-all kernels. So those are the kernels that dispatch and combine tokens across DP ranks for those for expert parallelism. So there's specialized ones, DPP low latency for decode and DPP high throughput for prefill. And it makes a big difference to optimize your engine deployment to use those kernels all the time, which you get from disaggregated serving. I saw there's one question in the chat. One thing I haven't understood is, are these features PD disag, i.e. already implemented in VLM? Why do we need a Ray implementation on top? Really good question. So yeah, you're exactly right. This is something that you could totally do in VLM, and or like just yeah by yourself in VLM. And there's a strong ecosystem of other offerings in general. I'll shout out Dynamo LLMD, for example, the LLM production stack. I think the benefit of Ray is that you can do this all in Python, and you also have actually it's kind of covered in more detail here, how we would distinguish the Ray serve LLM offering from Kubernetes. Um, but what we're trying to do is make it really easy to do this in Python with just a single Python script like this, or a YAML file for production. And I think if folks are more comfortable with the Kubernetes side, that's also one way to do it. Um, and yeah, and if they are looking to do more complex deployments and like combine like this deployment with multiple stages, like if you want to do some pre-processing or send it to different models in serial, something like that. It's something that's easier to do in Rayserve, we think. So yeah, that's like my nutshell answer, and would be happy to learn more. But yeah, yeah. So and then moving on, yeah, this is what it would look like in a disaggregated serving um, like Python file. We have a prefill config here where you specify your model ID and then whatever particular engine keyword arguments you want. In addition, you could add a prefix cache affinity router, which we have bundled in Racer LLM, that makes it, gives you the benefit of prefix cache reuse in amongst the ranks. And then also your decode config, you can just specify these completely independently, just as you would in typical LLM config in Racer LLM if you used it before. Combine them like this into a PD config, and then run and serve the app with the builder. So that's yeah, just like 40 lines of code. And yeah, otherwise you might be looking at some, Kubernetes YAMLs that are also like, I guess, totally reasonable. But there's some more benefits to using Ray that I'll touch on later, just in terms of observability and things like that. See, one more question. Is there a doc that outlines all the possible NVARs? Yeah, yeah, yeah. There's definitely, I think that just the VLM expert parallelism docs are decent for this. So let's see. Yeah, here's one, at least for the backend selection, the all-to-all backend selection. I'll drop this here. And hopefully that's helpful. Cool. All right. So with that covered, I'll move on to the demo portion. So here I have AnyScale. This is the like managed rate offering that like AnyScale offers. And here I'll walk you through the basic setup here. My head node is just a CPU only head node. And then I have two worker nodes here, both 4x And one thing I did was add a custom resource to these. So I labeled them prefill and decode. And so what this helps us with for now is limiting the DP replicas to land on a single node or a single set of nodes. And that means that the that's like a requirement on the VLM side that they land on the same node for now. And we're working on an enhancement to Array, so this um, custom resource won't be needed. But in terms of the uh, config, what it looks like is this. So I would add the prefill resource to my deployment config for prefill, and then the decode resource, deployment resource for decode. But otherwise, it's basically it's not too crazy. Oh, and then I meant to add that this is available through the here's the example code. So what I have here is basically an adapted version of this example code from the blog post. And walking through, I'm testing this with V2, with DeepSeek V2 Lite for the sake of hardware cost, but this example from GitHub was tested with DeepSeek V3. So briefly walking through it, we have you would probably start experimenting in Python is what we would imagine. So this is what it looked like in Python. You have your model ID, your deployment config, like I mentioned earlier, your custom request router, if you want to use that, and then all of your engine keyword arguments. So here we're enabling expert parallel load balancing, some configuration to the expert parallel load balancing config, um, optimizations to the compilation phase, and then our KV transfer config, which is Nixel in this case. And additionally, I've commented out for the DeepSeek V2 case, but this is just a variety of different environment variables you want to set, like you making like using DeepSeek's DeepGem, your particular all-to-all backend, and then for benchmarking, you might want to use a random routing and simulation strategy, etc. And then same for decode config, except here we would have set DPV low latency, and then put it all together with the PD DP OpenAI app. So this combines the YDP deployments. These are both enabling data parallelism. These YDP deployments with disaggregated serving. And then you can turn this all into a YAML as well. Right, this is a YAML for production if it's easier to maintain or deploy as a Ray service in Kubernetes. And it would look like this to run. This. You can run the YAML via serve run disaggregated YDP.YAML, and then it'll slowly come up. And then one benefit that I alluded to of using Ray is that even outside of AnyScale, you get this Ray dashboard that makes it really easy to see what's going on in your deployment. So you basically get the observability for free to know, okay, so this is my app, DeepSeek PD YDP. I have two DP rake assigners, one for the prefill config, one for decode. And then I have two replicas. This is my DP size for prefill and decode, the PD proxy server, and then OpenAI Ingress is the HTTP server that is fully OpenAI API compliant and then handles um, the endpoint selection amongst all the endpoints available. Cool. Okay. So it looks like we have this list of updated endpoints. Everything's green here. And then I'll just test it out with a query. Here's my query script here, just saying hello in a loop. And you can kind of see that this latency is longer than you'd expect if it was just if you didn't use data parallelism and expert parallelism, or you didn't use disaggregated serving. And so that's important to note in because the I think sometimes maybe these like solutions are put out as a magic bullet, but the communications overhead introduced by Nixel or introduced by the all-to-walls that need to happen between in an expert parallel deployment can start to eat into your throughput. The real benefit comes at higher concurrencies, higher batch size, um, situations where you have more than maybe 64 concurrent users or concurrent requests or 128, and you really want to maximize your KB cache and batch size. Cool. All right. Well, that is my demo. Any questions? Hmm. Okay. Yeah. Why is the YAML representation encouraged for prod? Can you talk about that more, please? So the ultimately it's up to it's up to the user to decide what works best for them. I think that like both the Python and YAML will um, work for putting out for standing up the service. But the benefit comes from like I think when you're yeah, okay, put it this way. If you're a machine learning engineer or a AI engineer and you're putting together this deployment and debugging and uh, assembling a pipeline basically of Python code, I think when you hand it off, you might what you might be doing is handing it off to someone who's on the inference side of things, might not know as much or want to know as much about the Python implementation. And what the YAML does is allow you to kind of abstract away anything that you want to be configurable, and hide any Python behind that in the YAML. So in particular, I think this example might not be the clearest way to show that. So like something to keep in mind. But in particular, here in the YAML, you have the import path, which imports from builder.py and imports this build PD OpenAI app assembler that takes this configuration and then makes it into a Ray service. Um, but like in theory, you could change this builder slightly to hard code all these arguments or most of them, and instead just expose, like what's something you might want to expose. Instead, you could just expose like the max model length or the maximum sequences. And so like an infra engineer or could edit just those items of a YAML and know that what they're touching is not too crazy, like, or is not going to affect the business logic too much of the deployment. Cool. All right. Just to keep it moving, I'll hand it off to Nikhil.
Awesome. Sounds good. Thank you, Seiji. Can you hear me okay?
Yep.
Sweet. Sounds good. Um, I'm going to be just talking a little bit about Ray data and specifically running like batch embeddings using Ray data. And I'll walk through a like super simple example for that as well. I think Seiji, you might have a question in the meantime if you want to answer while I figure out sharing my screen. Cool. Sweet. Okay. Can everyone see this example that I'm giving? Cool. Awesome. So before I walk through this, I'm just going to talk like briefly about Ray data. So I don't know, everyone's kind of might have different familiarity or whatever. And so essentially, this is kind of as a foil to the Ray serve LLM stuff that Seiji was just talking about. So Ray Data, independent of LLM stuff, is just a distributed framework for data processing that gives you kind of really good performance and also really good control by partitioning your data sets across workers, handling all of the parallel execution and stuff like that, and then also giving you kind of pandas-like data sets API for large scale, data transformations and processing. So it can be good for pre-processing ETL pipelines and basically just like also ML workloads that would need to scale beyond single machine memory limits, basically. And so what we have on top of that is Ray Data LLM, which is an extension on top of Ray Data that has a bunch of specialized processors for LLM inference. So it gives you kind of higher level abstractions to run models using engines like VLLM across distributed, GPU clusters, and gives you, model the ability to do like model replication, data parallelism, and just have automatic batching and partitioning as well there. Um, so I'm gonna quickly just kind of walk through this before running it and take any questions for anything that doesn't make sense. So what we have is a super basic demo. We have kind of a configuration object that basically controls how the LLM should process these embeddings. So we select a model, we have a very small model. Just for this, we specify kind of the task type, which can be for generating embeddings instead of text. You can also generate text. And then a few kind of keyword arguments for specifying how you want your engine to behave, right? So for the prefix caching stuff, like that's not as applicable for this because we're generating embeddings. We're not doing, handling repeated prefixes or anything. And for chunk prefill as well, like for super small batches, not as applicable. I think if you had sequences like longer than 1024 or 2048, you'd want to reduce kind of your memory spikes there as well. And we have, some L4s in our setup, 4 by L4. And so, but we've just scaled down the model length. Longer sequences will use more memory. I mean, you'll see that when you run these in the wild. And then as we go through, we can kind of set what we want our batch size to be, which is just how many kind of texts that we have here do we want to be processed per, GPU forward pass. And then you can kind of tweak these until you get, 80 plus utilization for the GPU memory. Um, and then we also have concurrency, which is a key one. So that's just set to the number of kind of parallel, model replicas or GPUs that you have. Since we have four, we can set ours to four, and each one will load a copy of the model independently, right? So this is not doing any advanced stuff that you would see with much larger models, where you would have to deal with things like tensor parallelism, pipeline parallelism, etc. Um, but those are all also kind of optimizations that we support. EP as well, which Seiji talked about. So we have a processor setup, which is just the build LLM processor, which is basically doing two things, right? So it has pre-processing and post-processing. For pre-processing, you convert something that has text and a bunch of text to something that has the prompt key and a bunch of prompts. VLLM expects that. Do we have any? Oh, that's about EFA. Okay, for Seiji. And then post-processing, which pretty much preserves the original text and extracts the embedding as well. So as we go down, um, doing the small test data that we have is handled by just automatically partitioning the data across the workers. There's a bunch of different kind of APIs that are exposed here for production use. Like you can use data.read Parquet, you can use data.from pandas, you can do data.read text. We just have a few that we're defining in memory here, so we're just doing from items. Um, and then when you actually call embedding processor DS, what happens there is basically four things, right? So Raydata is partitioning the data set across the workers based on your concurrency config. Two is each worker will be loading the model replica on its assigned GPU. And then three is you parallel process all of these batches. And four is you collect all the results back to the driver, right? So there's a couple of like notes here about how you'd want to handle this for single node versus multi-node, how if you want to make sure you're using all of your GPUs, and kind of the memory considerations you would have there. But that we can kind of address on a case by case. The main important thing are kind of the four configuration knobs that I mentioned earlier, which are just your batch size, your concurrency, your max model length, and then also whether you want to use like eager execution versus CUDA graphs as well. Um, a lot of the issues that you might like end up running into in the wild are the first one is definitely just ooms, right? So like CUDA ooms, CPU ooms, crashes, and they're kind of tweaking the knobs that I mentioned earlier are usually the way around that. The others are kind of looking at more performance-based stuff. So once you get it working, you might see things like lower GPU utilization. You might see slow throughput, things like that. You might see like really uneven GPU usage, things like that. For GPU utilization, like you can generally look at what the actual, you can do like a more fine-grained dissection and actually look at, the usage across GPUs, look at the actual decomposition of like where things are stalling, what the bottlenecks are. And you can also just look at what happens when you increase batch size up to the point where you start getting memory pressure. And you can also, add GPUs. If you have more GPUs, you can increase concurrency. Um, and you can also just make sure that if you go like before the GPU, you can make sure that the data pipeline itself is not the bottleneck, right? So you want to make sure that you're doing reads with parallelism as well. I think that is the majority of the things. There's obviously like you can use like NVIDIA NVI top, NVIDIA SMI. You can use the Ray dashboard as well, which I'll maybe briefly show. You can monitor the throughput as well. You can add your own timing and like statements throughout. But in general, using just GPU monitoring and using the Ray dashboard itself are probably sufficient for 80 to 90% of the use cases and the issues that people run into. Um, and so as I mentioned, also you can kind of have some flexibility in how you're doing your actual data loading. So you can just do it from like a local text file. You can have Parquet files as well, and you can deal with pandas, data frames as well. You can also do you can do streaming by using read text and configuring your parallelism as well. And this example that we have here is just taking few texts and then multiplying them and then doing some quick generation and showing one example here. So what I'll show is just kind of what that looks like, and then also what the Ray dashboard itself looks like as well. Um, and if there are any questions, happy to field those as well. The questions are mostly about networking, but if anyone has questions about data processing, happy to field those as well. So I'll just open up this dashboard. And you guys can't see that because I'm just sharing this, but I will share the dashboard as well. Yeah, so this will be running, setting up the engine, generating example of an embedding, and then killing the engine as well. So I'll start sharing the dashboard instead. So now you guys can see just what the Ray dashboard looks like. So you can see spikes just from what we've been running. This is the most recent one. And you can also kind of see that we've run this and you can view kind of all these metrics about your utilization, looking at node counts and things like that. I need to go to Grafana for that and actually look kind of at your jobs, at the submissions, and check out, performance, check out how quickly they finished, things like that. You can look actually at the actors. So the individual tasks that this breaks down into. You can do things like profiling. You can pull up a flame graph if you want to. It'll take a minute to render, but um, and yeah, so there's yes, these are the GPU task from earlier when we ran it with concurrency one, and yeah, so this is just a super basic example. And in this case, this was a model from Hugging Face that we pulled in answer to your question, Gordon. But you can also you can load your own models and have them stored in your in a on a node in a directory in a cache wherever you want. But for this example, we're pulling from Hugging Face. Um, and yeah, so there with Hugging Face, like generally you can specify a Hugging Face token and ensure that it's kind of passed through if you're doing multiple copies and things like that. You can also do some smart things with caching to make sure that you're not hitting Hugging Face every time. Hope that answers your question, Gordon. Um, and then I think, yeah, so basically, like if I'll just dig back into kind of the, I guess, semi-frequently asked questions, because these are things like I've run into when I'm trying to get some of our templates and stuff working, is basically like utilization is low, but concurrency is still high. So that generally would point to something like having too small of a batch size or having like a bottleneck somewhere in the data loading. Usually, I think a lot of people run into data loading issues. So looking at the worker or looking at the Ray dashboard, looking at your workers and seeing like what the idle times are, if you increase the batch size, or if you keep the original batch size, and also just making sure that you have sufficient parallelism when you're doing your data reading are kind of really good like first steps for getting an intuition. And then I think for configuration and tuning and stuff like that, generally if you're running into like data loading bottlenecks, just adding replicas is not really going to help for that. Or, like adding more GPUs is not necessarily going to help that if you're CPU bound. Um, and generally, if you do push your batch size like too big, you'll run into CUDA ooms, right? So that those are kind of the most frequent things that we see. Um, I think for this type of task, like this is obviously a very small model. In future ones, I might do something with like multimodal vision models or like large language models as well, just to show some of the trade-offs and configurations. Um, this model that I used obviously is like text only. So if you need like a vision language model like Quen or like Lava or something, you would need to actually just configure that and make sure that you are using the right like Ray data operators to handle the different input types for multimodal and things like that. Um, and yeah, so in terms of performance, I think you can create multiple processors and apply them separately, or use like the ds.map from Ray data with custom logic if you want to run like different models in parallel. The other thing is just like if you're doing operations that can be vectorized, like you'll use map batches instead of just map. And that's where a lot of the performance optimization and improvement comes from there. The other thing is we kind of have some reconfigured knobs and stuff that allow you to do more fine-grained configuration, per processor and per stage. And that allows you kind of good defaults, but the ability to go from good to even better, if you have like that insight into what your workload is actually doing. Um, yeah, so I think this is pretty much it for this time around. But I can give a more like in-depth deep dive if people are interested into like dealing with large models for